Okay, hi everyone, welcome back to this video series on Cisco ASA Firewall Simple Network Management Protocol, SNMP. SNMP is an application layer protocol that was developed to monitor the health of network devices. It has become a de facto standard because of its simple protocol design. A successful SNMP implementation requires a management station, also known as a manager, and at least one agent such as the Cisco ASA. The network management station such as Cisco Works monitors the agents by collecting the device and network information and presenting it in a GUI, which is graphical user interface. The agents, on the other hand, respond to the manager's request for information. If an important event occurs, the agent can also initiate a connection to the manager to send the message. The SNMP implementation uses the following 5 types of messages known as Protocol Data Units, PDUs, for the communication between the management station and the agent: get next, get response, set, trap. The network manager uses the management information base MIB to initiate the get and get next messages and request specific information. The agent replies with a get response, which provides the requested information if available. In a case where the requested information is not available, the agent sends an error detailing why the request cannot be processed. The network manager uses the set message type to change or add values in the configuration rather than retrieve the information. The agent replies with a get response message to indicate whether the change was successful. The trap messages are agent initiated to inform the network manager about an event, such as a link failure, so that an immediate action can be taken. Figure 3.6 illustrates the PDU communication between a security appliance as an agent and a Cisco Works server as a management server. As you can see here, configuring SNMP, the security appliance must be configured before a network management server can initiate a connection. Configure SNMP on a security appliance through ASDM by navigating to Configuration, Device Management, Management Access, SNMP, and following these steps. Step 1. Configure a global community string. A community string acts as a password when the management server tries to connect to the security appliance to get information. It is used to validate the communication messages between the devices. In ASDM, specify a global community string under community string default. If you prefer to use the CLI, set a global community string by using the SNMP server community command. Step 2. Set device information. Specify the location of the security appliance so that the SNMP server knows where the device is physically located. The security appliance enables you to set up contact information from an individual who is responsible for it. In ASDM, specify the device information such as the contact and ASA location options. If you prefer to use the CLI, use the SNMP server location and SNMP server contact fundamentals. Step 4. Define an SNMP server. You must specify an SNMP management server before the ASA can listen for polls or send SNMP traps. To define a new SNMP server, click Add under SNMP management stations and specify the following information: interface name. The name of the interface where the SNMP server resides. In most cases, it is inside or the management interface. If you select an interface other than the inside interface, ASDM generates a warning that you should consider about using an inside interface for security reasons. However, using a management interface is as secure if you have a dedicated management network IP address, the actual IP address of the SNMP server. The IP address must reside towards the interface selected UDP port. The security appliance uses UDP port 162 when it needs to send SNMP traps to the management server. If the SNMP server listens on a different port, you can change the UDP port on the security appliance by specifying a port under the UDP port option. SNMP version. The security appliance supports SNMP versions 1, 2C, and 3. Version 2C overcomes the deficiencies and problems associated with version 1. It uses the administrative framework of version 1 but enhances protocol operations by increasing security capabilities. SNMP v3 adds many security and remote configuration enhancements such as message integrity to ensure that the message has not been tampered with in transit, authentication to verify that the message is from a valid source, and encryption to prevent snooping by an unauthorized source. If you select SNMP version 3, you must define a username. If you select SNMP version 1 or 2C, ASA enables you to specify a host-specific SNMP community string server poll trap specification. The security appliance allows an SNMP server to poll information from the security appliance. It also sends event traps when unusual incidents occur. You can optionally restrict the security appliance to allow either SNMP polls only or traps only. In most implementations, an SNMP server is designed to poll as well as retrieve traps from the network devices. Step 5. Configure SNMP traps. The security appliance sends limited SNMP traps by default. However, you can configure it to send all supported traps or a superset of all traps. Do so by clicking the Configure Traps icon and selecting the following trap types: standard event traps. These traps include interface link up, link down authentication, and device cold start. IPsec event traps. These include IPsec tunnel, start and stop traps. Remote access traps. The security appliance generates a trap when remote access sessions reach threshold limit. Entry traps. These traps are sent when changes are made to the device, such as configuration, modification, or insertion, removal of hardware modules into or from the chassis. syslog traps. The security appliance sends syslog messages as SNMP traps to the management station. In figure 327, a new SNMP server is being added. The IP address of the server is 172.18.82.90 and it is located toward the MGMT interface. The server is configured to use SNMP version 3, which requires you to configure a username. The configured username is Cisco. So you can see here in figure 327, the SNMP SNMP server definition. And example 356, automatic saving of logs in the FTP server. SNMP monitoring. The show SNMP server statistics command is useful for checking the statistics of the SNMP engine. It displays not only the total SNMP packets received and transmitted, but also any bad or illegal packets handled by the security appliance. Example 357 displays the output of this command, where the security appliance received 12 GET requests and replied to all of them as GET response. As you can see here in example 357, output of show SNMP server statistics. Device monitoring and troubleshooting. Cisco ASA is loaded with a number of show and debug commands to monitor the health of the device and troubleshoot any network or device level issues. CPU and memory monitoring. The show CPU usage command indicates current CPU utilization. It displays an approximate load over 560 and 300 seconds. In example 358 shows that the 5-second utilization is 2%, whereas the 1 minute and 5 minute utilizations are 1%. The security appliance can display memory usage through the show memory command. It shows a summary of the available and allocated memory in bytes and as a percentage. In example 359, the free memory on the security appliance is 849.120.760 bytes, 810 MB. And the allocated or used memory is 224.621.064 bytes, 214 MB. The total memory on the security appliance is 1024 MB. The security appliance can display the system buffer utilization if the show block command is executed. When the security appliance boots up, the operating system carves out memory to create the maximum number of blocks for different block sizes. The maximum number of blocks does not change except for the 256 and 1550 size blocks. For these blocks, the security appliance can dynamically create more blocks if necessary. The security appliance allocates a block from the pool when it needs to use it, and it returns it when it is done using it. There are 11 different sizes of buffer blocks, and each buffer type is responsible for handling specific packets. Type 3.8 shows the buffer block sizes and provides a brief description on where they are used. When you run the show block command, the security appliance displays the following counters. Max indicates a maximum number of blocks available for a specific block size. Low indicates the lowest number of blocks available at one point since the last reboot or the last time the counters were cleared by the clear block command. A low count of 0 indicates that the security appliance had run out of buffer space for a particular block at some point since the last reboot or the last time the counters were cleared. C and T displays the currently available blocks for each block size. So you can have a quick look at this here, table 3.8 buffer sizes. In example 360, the security appliance has allocated 300 blocks for the 4-byte block size, and it is currently using 1 block. The low counter is set to 299 because the security appliance has allocated only 1 block of it since the last reboot. Using ADSM, you can monitor the health of a security appliance by navigating to monitoring, properties, system resources, graphs, and selecting a graph for block use, CPU utilization and memory use and availability. Troubleshooting device issues. Cisco ASA provides a number of troubleshooting and diagnostic commands for troubleshooting traffic as well as device-related issues. Troubleshooting packet issues. In any firewall deployment, administrators spend most of their time defining new policies and troubleshooting packet flow issues. The following sections discuss 3 scenarios to show how the security appliance assists in troubleshooting those issues. Tracing packet flow. To learn which processes are being applied to a packet flow, use the packet tracer feature. Using this feature, describe how a packet should be structured based on the IP protocol source and destination IP address and the source and destination ports. The security appliance provides information when the packet goes through different processes such as the access control lists, ACLs, routing and address translation, NAT. Each process inspects the packet individually and decides whether it needs to allow or deny that packet. Use this feature by choosing Tools, Packet Tracer and specifying the interface from which the packet should be coming, the IP protocol and the source and destination IP addresses and ports. As illustrated in figure 328, the administrator is tracing a TCP packet source toward the inside interface from 192.168.10.50 and destined to 209.165.200.229 and a source port of 1024 and destination port 80. Each process checks the packet and allows it. The end result is successful and that packet is allowed to pass through the security appliance. Example 361 shows the CLI equivalent of figure 328, capturing packets. One of the most robust features in the security appliance for troubleshooting traffic-related problems is the packet capture feature. When packet capture is turned on, the security appliance sniffs interesting traffic and stores it in the buffer. This is important if you want to confirm that traffic from a particular host or network is reaching the interfaces. You can use an ACL to identify the type of traffic and bind it to an interface by using the capture command. The captured packets can be viewed either locally on the security appliance or on an external device such as Wireshark if you export the information to PCAP in format. In figure 361, an ACL called inside capture is set up to identify packets sourced from 209.165.202.130 and destined for 209.165.200.230. The security appliance is using this ACL to capture the identified traffic on the inside interface using a capture list named cap inside. To view the captured packets, use the show capture command followed by the name of the capture list. In example 362, the security appliance captured 15 packets that matched the ACL on the inside interface. The highlighted entry shows that this is a TCP SYN show as S after the destination port. Packet sourced from 209.165.202.130 with a source port of 11084 and it is destined for 209.165.200.230 and a destination port 23. The TCP window size is 4128 and a maximum segment size MSS is set to 536 bytes. The output of the capture command can be exported to PCAP format, which can be imported into a sniffing tool such as Wireshark or TCP dump for further analysis. To download the file in PCAP format, use HTTPS IP address of ASA/capture/capture name /PCAP in a browser. For example, to download the PCAP file for the capture defined in example 362, use https://172.18.82.64/capture/cap inside/PCAP. Monitoring dropped packets. The security appliance, being a firewall, drops packets if they do not adhere to an enterprise's security policy. These drops could be related to the deny statements in the ACL's illegitimate VPN packets, a malformed TCP packet, or a packet with invalid header information. In some cases, you will want to get the statistical information about the packets or connections dropped by the security appliance within its accelerated security path ASP. Use the show ASP drop command as shown in example 363, which shows that over 57000 packets were dropped because of the deny statement in ACLs. You can see that the security appliance has dropped over 57,000 packets because they were denied by the ACL. About 300 packets were dropped because the adaptive security appliance received a non-SYN packet as the first packet of a connection. This usually occurs when the client and the server believe that a connection was opened, but the firewall has already closed that session. Finally, the security appliance dropped 3 packets when the interface was shut down. Troubleshooting CPU issues. If you are monitoring your CPU utilization and it is constantly running high, you can activate the CPU profiling feature on the security appliance by using the CPU profile activate command. You can also allocate memory for storing a specific number of samples, which can vary from 1 to 100,000, with the default being 1,000. The more memory you allocate to this process, the better the accuracy for CPU profiling. After CPU profiling is activated, use the show CPU profile output to view the output. Unfortunately, you have to send the output of this show command to attack engineer for analysis. So I'm going to leave it here today for this video. If you like listening, please consider like, sharing and subscribing. Thank you.